Okay, so today I wanted to talk about very basic stuff in homological algebra in an elementary topos, but actually most of the time we will consider only Grothendieck topoi because they have a sufficiently nice form of their category of forbidden objects. But in general, under some conditions, like sufficiently many injective objects, what I will say goes through for an arbitrary elementary topos. Okay, so let's start from a short introduction of Levier theories. So an algebraic theory or Levier theory is a category T with finite products, which is generated under this finite products by one object. Namely, it's usually denoted by 1. So objects of T are in bijection with non-negative integers corresponding to powers of 1. And the language of Levier theories is quite convenient because it allows us to present many familiar notions of algebraic theories. So some examples. So first of all, we have the initial Levier theory. Yeah.
What do you mean by the category which is generated by this element, this object?
Well, it just means that any object in this category T is of the form 1 to the power of n for some n. So this means that the object generates this category and the products. So each object is a product.
Yeah. What is the power?
Well, it's just like this. So it's product of 1 with itself n times.
Okay, thank you.
Yeah. So yeah, let's see some examples. So first of all, we have the initial Levier theory, which is a theory of sets, and it's algebraic. Well, this category T in this case is just the opposite category of finite sets. So since it's an opposite category and finite sets, well, I mean, we take the skeleton of finite sets so that we don't have any stupid problems. But since finite sets are generated by a singleton set under coproducts, the opposite category is generated by the singleton sets under set under products. So S of 1 is just a singleton set, and well, this object generates the category S under products. Well, and similarly, it is well, we have these sets of morphisms. So since it's an opposite category, we have to transpose two arguments. More interestingly, we can encode theory of groups using Levier theories. So Levier theory for groups is just a category where an object indexed by n corresponds to a free group on n generators, and a Hom set between an object indexed by n and the object indexed by m is just the set of group homomorphisms between two free groups. And of course, we can also encode abelian groups. So here, instead of free group, we have free abelian group of rank n, and the set of morphisms is given by homomorphisms of abelian groups.
So the set of morphisms consists of all of arbitrary morphisms in set, yes?
Yeah, arbitrary homomorphisms.
Yeah. Okay.
Yeah. Arbitrary maps of sets. Yes, that's correct. Yeah. You can also see that you can obtain both these two theories by some kind of reconstruction from this theory of sets. So you can just apply the free functor to each object and obtain these theories. Okay. So some maybe less trivial examples consist of associative algebras, Lie algebras, and some other examples that we won't cover today, but there are plenty. So for associative algebras, we just consider free associative algebra generated by n elements as an object indexed by the number n. And as morphisms, we just consider all homomorphisms of algebras between two free associative algebras. And similarly, for Lie algebras, we just consider free Lie algebra on n generators. And then we consider as a set of morphisms all Lie algebra homomorphisms between two free algebras. Obviously, using the freeness, we can reduce this to just homomorphisms from Lie algebra on one generator to Lie algebra on m generators to the power of n. But yeah, that's just a trivial remark. Okay, but another reason why Levier theories are so useful is that actually we have a very nice notion of an algebra over a Levier theory, which immediately generalizes to an arbitrary topos. So assume that we have a topos E, then a T algebra in E is just a product preserving functor from T to E. So if we consider E to be the topos of sets, we get the usual T algebras. So for example, we get the usual groups, the usual Lie algebras, the usual abelian groups. But if we consider some more interesting topos than just sets, we obtain group objects or abelian group objects or Lie algebra objects in some non-trivial topos. So for example, we can take sheaves on some scheme and we will obtain group objects in sheaves on a scheme. And that's very nice because it's an immediate generalization. We don't need to draw some diagrams and say that, I don't know, they commute or something like that. We just say that we have a functor which preserves products and it immediately encodes the structure of an object over this Levier theory in a topos. So that's the reason for this approach to defining algebraic objects inside of a topos, so that we can immediately generalize from sets to arbitrary topoi. Okay, so some more examples. So if you consider,
sorry.
Yeah.
Could you return to the definition?
Mm-hmm.
In this definition, the algebra is a product preserving F. What is F?
Product preserving functor.
Product preserving functor. From T to sigma.
Yeah.
From E to E. Okay.
Yeah. Okay, so for the theory of groups, we obtain, as I said, group objects in the topos E. For the theory of abelian groups, we obtain abelian group objects in E. And for Lie algebras, we obtain Lie algebras in E. And as a concrete example of this, we can obtain Lie groups as algebras over Levier theory of groups in the category of sheaves on manifolds. So those will be not only the classical Lie groups, but infinite dimensional Lie groups as well. So if we consider group objects in sheaves on manifolds, we obtain all classical, i.e. finite dimensional Lie groups, and also, for example, Lie groups of the form, I don't know, C infinity from M to some finite dimensional Lie group. So this is an infinite dimensional Lie group, and automatically it's a group object in the category of sheaves on manifolds. Okay, and similarly, of course, for abelian Lie groups, we just consider product preserving functors from theory AB to the Topos sheaves on manifolds. Okay, so now we're ready to give a setup of homological algebra in a topos. So assume that we have a topos, by which I mean an elementary topos, and denote by AB of E the category of internal abelian groups in E, but that's just abelian, well, algebras over AB in E. So that's just the category of algebras. Okay. And
sorry, internal?
Yeah. But that's just, well, those are just basically words, because the word internal means that you can draw diagrams in sets which encode the structure of, for example, abelian group, and then you can consider them as diagram in an arbitrary topos. And then you say that an object which satisfies these commutativity conditions for these diagrams is an internal, I don't know, abelian group in a topos. But a more concise way to do this is to say that an internal abelian group in E is just the product preserving functor from this Levier theory into E. So you don't have to give some deep meaning to the word internal abelian group. It's just the product preserving functor. Is it satisfactory? Okay. Yeah, okay, great. So basically all of our homological algebra will happen in this category, which, as we'll see in a moment, is actually an abelian category. And if E is a Grothendieck topos, then it's even a Grothendieck abelian category, meaning that has extra nice properties. Okay. So what is a Grothendieck abelian category? Well, an abelian category, meaning that it is an additive category with kernels and co-kernels, is a Grothendieck abelian category if it satisfies two conditions. So first of all, the category should have direct sums, and filtered colimits should be exact, i.e. they compute with finite limits. Yeah, so this is known as AB5 condition because of the list of conditions in Grothendieck's Topos paper. But another condition that we need for an abelian category to be a Grothendieck category is that A should have a generator. So a generator is an object in A such that for any for any proper sub-object in another object M, we have a morphism from U to M such that it does not factor through M. So that's the definition of a generator. And I guess it can be reformulated in terms of conservative collections, but I don't think that we'll need this. Maybe we'll discuss it some other time, but the idea is that a generator or a collection of generators in a category is sort of a collection of test objects that allow you to distinguish morphisms. So since we're working in a setting of abelian categories, it is enough to require this thing about subobjects, but in general it's a bit more in general, it's a bit more general, meaning that we consider a wider class of morphisms, not just inclusions of sub-objects. But that's a story for another time. Okay, so we have these two conditions which ensure that our abelian category is nice. And we have the following theorem. So if E is an elementary topos, then the category of abelian objects, abelian group objects in E is an abelian category. And if E is a Grothendieck topos, then this category is a Grothendieck abelian category. So let me give a very brief sketch of proof of this theorem. So first of all, finite limits in this category of abelian group objects are created by the forgetful functor from the abelian group objects to E. By definition, an abelian group object is a product preserving functor, and the forgetful functor just maps A to the value of A on the object indexed by 1. So in other words, that's Z, free abelian group on one generator. And this forgetful functor creates finite limits in the category of algebras over the theory AP. Also, we can prove analogously to the case of sets that the initial and terminal object coincide, so they exist by axioms of the topos, and they coincide in ways similar to the case of sets. Also, similarly, we can prove that binary products and full products coincide, and we can denote them by direct sums. Then another thing is
sorry.
Yeah.
Sorry, could you recall? Can we? How can we create finite limits? With the help of this forgetful functor.
Well, just means that you can compute limits at the level of the underlying objects in the topos. So for example, a limit of abelian groups, if we consider that the topos of sets, is just the limit of the underlying sets, which naturally becomes a group. So the idea is like this.
Yeah, and there are no problems here. Yes.
No, there are no problems.
Okay.
I guess you can do this even for like an arbitrary linear theory. It's not specific to abelian groups. So, yeah, that's just basically that's just the property of the forgetful functor from algebras over Levier theory to the ambient category. So it creates finite limits. Basically, it follows just from the fact that finite limits, well, and limits in general, I guess, commute with products, and this means that if we want to obtain a product preserving functor, which is a limit of the family of product preserving functors, then we can do it by taking a limit in the underlying category and then saying that, well, limits compute with finite products, and we obtain a product preserving functor in this way. So I guess this works in great generality.
Okay.
Okay, so co-kernels in the category of abelian group objects in E can be computed like this. So we can take co-equalizers of the following pair. pairs of morphisms. So we take a composite morphism like this, and then and also we take a projection, and we obtain the co-kernel of a morphism between abelian group objects. This implies that if we have a monomorphism in category of abelian group objects, then we can compute it as a kernel of the map to the co-kernel, which is a familiar property for abelian groups, for example. And also, we can derive that epimorphisms in the category of abelian group objects coincide with epimorphisms in the underlying category. And from that, we can see that every epimorphism is of the form co-kernel for some morphism F, which is necessary to show that the category of abelian group objects is an abelian category itself. Okay, so now assume that. Basically we checked that kernels and co-kernels exist, and that hence that our category of abelian group objects is an abelian category. So now assume that we're in a setting where E is not an elementary topos but a Grothendieck topos. Then we know that filtered limits compute with finite limits. Actually, it can be stated in even greater generality that shifted limits compute with finite limits. No, sorry. That's not correct. Okay, we just know that filtered limits compute with finite limits in any Grothendieck topos. That's a fact. About shifted limits, forget it. They compute with finite products, not finite limits. And this means that our condition AB5 is satisfied. I also assume that to show that our category of abelian group objects in E has a generator, consider a collection of generators for E, which also exists by the properties of a Grothendieck topos. And then we can take a free abelian group, or to be more precise, a free abelian group object in E, generated by the co-product of these generators. Then we obtain a generator of the category of abelian group objects in E. So I guess I should have mentioned that this is a very general setup, that if we have a Levier theory, then we have a free forgetful adjunction for an arbitrary topos. So if we take T algebras in E, then we have on one hand a free functor from the category E, and on the other hand a forgetful functor from the category of algebras. So the forgetful functor works as we described before. It just takes the value on the generator of T, and the free functor is its left adjoint. So it also works as expected, but sometimes it's hard to give an explicit formula for it. But it is characterized by the universal property of a free functor.
Sorry, what is the intuition of generators of some topos? Or you mean these generators of generators as a category generators, or something
No,
else.
generators as category generators. Well, the intuition is like this. So assume that we have a category of sheaves. Then to know the value of a sheaf on an arbitrary other sheaf, it is sufficient to know its value on representables. So in a sense, the collection of representables is the collection of generators for the Grothendieck topos. But it can be smaller, of course. But the idea is that generators are sort of test objects that define an arbitrary sheaf. So that's the intuition.
Thank you.
Okay, great questions. Thank you so much for asking. Yeah. Okay. So that was a kind of a sketchy proof of the fact that if we take the category of abelian group objects in a topos, then we obtain an abelian category, and moreover, if it is a Grothendieck topos, then it's a Grothendieck category. Now, let's discuss one more thing, that if we have a geometric morphism between topoi, then it descends to an adjunction between categories of abelian group objects. This follows from the fact that both f lower star and f upper star are left exactly, that they preserve products, hence they preserve product preserving functors, and this means that we have an adjunction between categories of algebras over, well, basically over any linear theory. So also we have the following facts. So f lower star preserves injectives in the category of abelian group objects in F. And if F is surjective and the category of abelian group objects in F has enough injectives, then the category of abelian group objects in E also has enough injectives. Now, I remind that enough injectives means that any object in a topos can be, or in a category in this case, can be embedded, or there is a monomorphism into an injective object. Okay, so yeah, the first part is precisely as I said. So since both functors are left exact, they preserve products. This means that they preserve T algebras for Levier theory T in particular. For a Levier theory of abelian objects, abelian group objects, they are also preserved, and we have an adjunction between categories of algebras. So for the second part, that f lower star preserves injectives, consider an injective in the category of abelian group objects in F, and consider a diagram like this. So we want to find.
I'm sorry. Could you please show the previous slide one more time?
Yeah, sure.
Okay, thank you.
Okay. Yeah. Please stop me if something is unclear or you just want me to slow down. Thank you for doing that. Okay. So we want to show that the image of an injective object is an injective object itself. For this, we consider a diagram of this form, and we want to find a lift like this. And we do a very standard thing. We just apply the adjoint functor. We consider a similar diagram since the unit of the adjunction is always monic. I didn't prove this, but that's another fact about geometric morphisms of topoi.
So
this means,
why we have a lifting?
Here, well, just because E was injected.
Oh, okay.
Thank
you.
We want to show that the image of an injective object is injective, and for this we just apply the adjoint functor. We consider this diagram in the category F, or category of abelian group objects in F. There, the lift exists by assumption, and then we just apply f lower star to map this lift to a desired lift in the category of abelian group objects in F. This works like this, a pretty standard play with junctions. Okay, so now let's consider this question about having sufficiently many injective objects in a category of abelian group objects. So assume that we have an abelian group object in E. We know that there exists an E in abelian group objects in F such that the image under F upper star of E embeds into E. So now to find an injective envelope of A in the initial category EB of E, we just apply F lower star, use the fact that the unit is always monic, and the fact that F lower star preserves monomorphisms. And thus we obtain by the previous result that an image under F lower star of injectives of an injective is an injective, we obtain an injective envelope of A. Okay, so that was another sketchy proof. Now let's discuss something, I guess, a bit more esoteric, and that is axiom of choice in topoi. So the fact is that I don't know, at least for me, the phrase axiom of choice has bad reputation because I think of logic immediately, and this bores me to death. But actually, we can formulate an axiom of choice categorically in very simple terms, saying something about sections of epimorphisms. And if you think about it a bit, actually, that's precisely what we do in ordinary set theory when we say something about axiom of choice. So assume that we have a topos E and we have an arbitrary object X in this topos. Then we have a partially ordered set of subobjects in X. So the partial ordering comes from monomorphisms between two subobjects. So we consider monomorphisms over X. And then we have, well, obviously any partially ordered set can be considered as a category, as a lattice, and we have an inclusion of this, an embedding of this lattice into the over category, or into the slice category of E over X. And we also have left adjoint of this embedding, which is called the support functor of an object over X. So this works like this. We take an object over X, and then we take the image of this morphism. So that's another thing that we didn't discuss in detail, but in our arbitrary elementary topos, we have an epimono factorization. So each morphism factorizes as an epimorphism followed by a monomorphism. And we take precisely the image of this epimorphism, it's called an image of a morphism. And this support functor maps an object over X into image of the corresponding morphism. And we say that support split in E, or that E satisfies epsilon SS, if for any object in E, a morphism for an epimorphism from X to sigma with respect to 1 over X is split. So obviously we have a support functor which corresponds to the terminal object in our topos, and this string produces subobjects of the terminal object. And by definition, we always have an epimorphism from X to sigma 1x. And obviously, the term split epimorphism means that we have a section for this epimorphism, and moreover, the domain of this epimorphism splits as a co-product of for example, an image of this section and something else. Okay. So we say that the topos E satisfies axiom of choice if for any object in E, the slice topos satisfies the axiom of splitting support, or the axiom SS. So let's consider an example. Assume that we have a well-ordered set. Then the category of functors from P to sets satisfies the axiom SS. For such a functor, we can consider sigma 1 of x. Basically, by definition, it consists of such it consists of it is a set which consists of P in P large such that x of P is non-empty. And since it is a well-ordered set, it has a minimal pi zero, and then sigma 1 of x is just the image under the unit embedding of pi zero. So I guess in more down-to-earth terms, that's just the collection of elements in pi large which are less or equal than pi zero. But this topos of functors does not satisfy the axiom of choice. So it is a facet of Russell type paradox that if we have a category of functors like that, we can consider a very simple well-ordered set which just consists of two elements, and we can consider y, which is a constant diagram which corresponds to this set itself, and we can also consider an x which has the following two values. So on 0 we have a value p, and on 1 we have a value of a singleton set. And we have an epimorphism from y to x, which is given by object-wise epimorphism. And this epimorphism can be easily seen to not split in any shape or form, which means that this category, this topos, does not satisfy the axiom of choice. Another example, I guess, would be a category of sheaves over a circle. Then we can consider a sheaf of sections of a two-sheeted covering of the circle. So we have the two-sheeted covering, and we consider the sheaf of sections of this map. And obviously, locally it is epimorphic on the terminal sheaf, which corresponds to the unit embedding of x itself, because obviously two-sheeted covering is locally epimorphic. But there are no global sections of a two-sheeted covering, which means that the morphism from y to x does not split, or from y to to the terminal sheaf, which means that the category of sheaves over topological space does not necessarily satisfy even the axiom of splitting support. So yeah, just an example. But actually, we can characterize the topoi which satisfy the axiom of choice, and in a sense, they're not very interesting and very satellite. So first of all, let's consider an algebraic structure on the subobject classifier omega. So we have three binary operations on omega. First of them is given by the intersection, which corresponds to the subobject, which is to the subobject of the product, which is given by the product of T and T, where T is the subobject classifying morphism. Then, if we have a subobject like this, then we have a classifying map from omega squared to omega, and this is precisely this binary operation of intersection. Similarly, we can define a union, or this co-product on omega, which is given by taking the product of the terminal objects. This is a subobject of omega times the terminal object in one. So omega times 1 and 1 times omega. And then we can take the co-product, which corresponds to the union of Topos theoretic union of these two objects. And this is a subobject of omega times omega, and we take the classifying map and we obtain this co-product operation on omega. And also we have an implication operation on omega, which is also binary, and it is defined as an equalizer of the co-product or the conjunction and the projection on the second part. Okay, so we have these three operations, and also we have a unary operation of negation, which corresponds to the classifying map of the complement to the subobject classifying morphism. So I guess we'll need a separate talk discussing the complements in topoi, because it is somewhat unexplained as of yet what is F, but you can think of it as a complement of T. So T is a subobject classifier, and F is something complementary. It's a whole thing. So it's called Levier-Cherny topology on a topos, but unfortunately I want to get to some homological algebra today, so I won't discuss it in detail. Okay. So I want to discuss it in detail, but just think of it as some kind of complement. Obviously, for sets, it's quite clear what is F. So for sets, we have 1, and the subobject classifier consists of precisely 2 elements, and one of them corresponds to the subobject classifying map. So one maps to 1, and another corresponds to this map F. So 1 maps to 0. Okay. So now we can define what is a Boolean algebra or a Boolean ring. These are not completely the same, but their models are always equivalent, so I won't distinguish between them very much. But the idea is that we can define a Levier theory of Boolean rings like this. So the value on an integer n is a group ring of a free monoid with idempotems with coefficients in F2. So a free monoid with The importance is just the quotient of the usual free monoid on n generators by the relation that the square of each element equals this element. And then the morphisms between two objects are given just by morphisms of algebras. Another way to define what is another way to define this category dA is to consider the category of finite sets of cardinality 2 to the power of n, and it can be seen that these produce equivalent categories of algebras always. So the basic idea is that these monoids with idempotence encode the algebraic structure on power sets of n element finite sets. So 2n corresponds to a power set of n element finite set, and this means that we can endow such a set with an algebraic structure which corresponds to intersections, unions, stuff like that. So the correspondence between this algebraic definition via algebras and this sort of set theoretic definition via intersections and unions is given by this. So conjunctions correspond to multiplication. Disjunctions correspond to these things. The order relation corresponds to the fact that the multiplication, well, the product of x and y is equal to x, and the sum. So the sum here corresponds to the symmetric difference of two elements, which is just the disjunction of two elements and the negation of this disjunction. That's right. Okay. I'm not sure that it's the correct formula, because for sets it gives something stupid. What do you think? No. Don't write that at all. Let me write it down a bit differently. So it's disjunction of okay, yeah, that works a bit better. Okay, so we have this correspondence between set theoretic or object-wise operations and algebraic operations, and this is all very abstract, so it's a linear theory, and we can define internal Boolean algebras for an arbitrary topos because of that. And so now we arrive to the notion of a Boolean topos. So a topos, okay, so for a topos, the following conditions are equivalent. So first is that omega under operations described above is a Boolean algebra or a Boolean ring, or an algebra over the linear theory of finite sets of cardinality 2 to the power of n. All these things are equivalent. Another condition is that the double negation is the identity map on the subobject classifier. Yet another condition states that if we have if we have a subobject of x, then there exists a complementary subobject, so that x splits into a disjoint union of x prime at x2 primes. And finally, that the subobject classifier splits as a co-product of two copies of the terminal object. So that's why Boolean topoi are, so a topos like this is called a Boolean topos, and that's why Boolean topoi are so much like sets. So in sets, we have this description of the subobject classifier. And in arbitrary Boolean topos, we also have this description. And in a sense, Boolean topoi are discrete. So as you can see, any object splits into a subobject and its complement. And obviously this only works if we have some sort of discreteness, which is characteristic of sets. So in sets, we don't have any problem splitting a set into a subset and its complement. But if we consider, for example, open subsets or some sheaves on local, we obviously can't split it like that. But as the following theorem due to bar shows, actually each Grothendieck topos can be resolved to a Boolean topos. So maybe the topos itself is not discrete, but there exists an epimorphism from a Boolean topos into this topos, and yeah, this sort of shows that yeah, any topos has a covering Boolean topos. But first, we have the following characterization of Diaconescu, which states that if a topos satisfies an axiom of choice, this means that this topos is Boolean and vice versa. So the condition of being Boolean is equivalent to axiom of choice. And as I said before, the theorem of Bar states that any Grothendieck topos can be covered by a Boolean topos, which in a sense is unsurprising because I guess if we think of topoi as categorical generalization of topological spaces, then obviously for any topological space there exists an epimorphism from a discrete topological space into this topological space, which is just given by taking a topological space and endowing it with discrete topology. Okay. So another nice thing about this result of Bar is that actually some questions about an arbitrary Grothendieck topos can be reduced to the questions about sheaves on a complete Boolean algebra. So if B is a Boolean Grothendieck topos, then it is actually equivalent to a category of sheaves on a complete Boolean algebra with canonical topology. So canonical topology is the largest such topology that all objects are representable. Sorry, I said something very stupid. All representable functors are sheaves. But for complete Boolean algebras, we can also give another description. The open subsets are just subsets of elements which are less than or equal to a fixed element. So this kind of atomic topology. Okay, so the idea of proof of this result is that if we consider a site from Topos theorem, then for a Boolean, because for a Boolean topos, any category of subobjects is a Boolean algebra, and even more, it's complete Boolean algebra. This means that after sort of gluing them together, which is the procedure we use to construct a site in Topos theorem, we once again obtain a complete Boolean algebra. So that's just a very rough idea. Since we didn't discuss Topos theorem in detail, I'm not trying to explain it rigorously, but the idea is that basically Girard's theorem operates with categories of subobjects, and for Boolean topos, categories of subobjects are Boolean algebras, which allows us to construct B as sheaves on some Boolean algebra. Okay.
Sorry, sorry. What is the target of sheaves? Of sheaves?
Sets, or maybe
sets. Mm-hmm.
Yeah. We're right now we're dealing with just ordinary topoi, not higher topoi, and therefore we consider set valued functors. Yes. Thank you for the question. I guess it will become relevant later that actually we can consider not sets but simplicial sets, for example, and obtain higher topoi. But right now we consider just set valued functors. Okay. So now we arrive to something about homological algebra at last. We have the following theorem. Assume that we have a Grothendieck topos, and then the category of abelian group objects in E has enough injectors. And the way we go about proving this theorem is the following. So as we said earlier, by Barr's theorem, we can replace the Grothendieck topos by a Boolean topos and use this proposition from before, which stated that if a topos which maps into our topos epimorphically had enough injectives, then our topos also has enough injectives. And that's precisely how we operate. And we just this means that we can consider just some Boolean topos and prove this result for a Boolean topos, and this will imply the result in general. So assume that E is Boolean, then we can do pretty much the same thing we do for sets. So we have an equivalence. An object is injective if and only if its value on each object in this Boolean algebra B thick is a divisible abelian group. So since we consider functors in sets, evaluated sets, a value of E on individual objects are just abelian groups, and we have this equivalence. So an object is injective if and only if each of these individual values are divisible abelian groups. This is proved completely analogous to the case of sets. Then we can consider the following sheaf. So we can take, we have two ways of doing this. So either we can take a constant pre-sheaf which corresponds to this abelian group, and then we can sheafify it. Or we can consider an internal object of integers and internal object of rational numbers. So an internal object of integers is just the free functor on the terminal object, and the internal object.
Sorry.
Yeah.
This is proof of what?
This is proof of the fact that we have enough injectives in the case.
We continue the proof. Okay.
Yeah. So we established this characterization, sort of established. I just stated that it exists. I stated that there is a characterization of injective objects as divisible on each object, as sheaves such that their values on each object is a divisible abelian group. And now we will basically use the fact that in abelian groups there is enough divisible abelian groups to embed an arbitrary abelian group into a divisible one. So
okay.
To do this, we just construct an analog of the prototypical divisible abelian groups, which is just the quotient of rationals, which can be defined.
This one is a divisible one. Yeah.
Yeah. And then basically we just say that just as in the case of ordinary abelian groups, if we have an abelian group object in the topos, then we can embed it into a sufficiently large power of this rational circle, and that basically completes the proof. So we sort of reduced the question about an arbitrary topos first to a Boolean topos, and then from a Boolean topos we just reduced it to the case of sets. So that's a very rough idea of what happened here.
What is A?
A is just an arbitrary abelian group object.
Okay.
But yeah,
I mean a small of this.
That's the sheafification factor. So you can consider a constant pre-sheaf. So if you have any abelian group, then you can take a pre-sheaf that has value equal to this abelian group on any object of our site. But then you need to sheafify it to obtain actually an object of our topos. So that's why we have this thing here. That was just an explanation how to construct this rational circle in an arbitrary topos, an arbitrary Boolean topos. So we just either take an internal object of rationals and mod out by an internal object of integers, or we take an external object of rationals, mod it out by external object of integers, then take constant pre-sheaf and then sheafify it and obtain the same.
So the quotient is some category, or
no, the quotient is once again an abelian group object in our topos, because as we saw earlier, category of abelian group objects is abelian, and that means that we can take quotients. We can take co-kernels. So this is just the co-kernel of.
Okay, and the bar line means what?
It means the constant pre-sheaf.
So constant. It means that we have the same value.
Yeah. So if we have this, so if we have an object of our site, then the value on this object is precisely this abelian group. Yeah.
Okay. Thank you.
Mm-hmm. Thank you for the questions. Yeah. Okay, so now finally we can say what is the cohomology in the context of topoi. So first of all, why cohomology? Well, because an arbitrary topos usually does not have enough projectives. To have projectives, basically on a very rough level, you need to be able to choose generators. So how do you usually construct a free or a projective resolution? You take a map from a free module, for example, which is spanned by generators of your arbitrary module. Then you take the kernel of this map, you choose some generators in the kernel, you map from another free module, and so on. And you obtain a projective resolution. But since axiom of choice fails in an arbitrary topos, we can't do such a thing. So we only have injective resolutions, and injective resolutions are only good to defining cohomology and not homology. So that's an explanation of the fact that we consider cohomology in topoi. And now let's define what is cohomology in a Grothendieck topos. So assume that we have a Grothendieck topos E, or actually it's not important. We can just consider an elementary topos with enough injectives. It's completely irrelevant. The structure of a Grothendieck topos is completely irrelevant at this stage. then we can define the cohomology of these topos with coefficients in an abelian group object in this topos as right-derived functors of global sections of this sheaf, so to speak. So global sections are just is just a functor from abelian group objects in E to abelian groups, which is given by this. So we take morphisms from the terminal object into this functor. So if you think of, for example, topos of sheaves on a topological space, then this precisely corresponds to global sections. So we take all sections over the whole topological space, because in sheaves on topological spaces, the terminal sheaf precisely corresponds to the unit invasion of the whole space. And so cohomology is defined like this. We just take a right-derived functor, which can be computed using injective resolutions, and we obtain the notion of a cohomology of a topos with coefficients in an abelian group object in this topos. And another way to describe it, which is standard homological algebra, that we can describe cohomology or right-derived functors of Homs as X functors in this abelian category, and we can, for example, use the Yoneda's description of X functors to do that. Yeah, so we have this alternative description, and also we can refine our definition. And for an arbitrary object in our topos, we can consider coefficients. We can consider a cohomology of this object with coefficients in A. So to do this, we just restrict to the slice topos over X, and we obtain, well, we have an adjoint pair of functors between the slice topos and the initial topos. So one of them is a forgetful functor, and another one is the pullback functor. So it's basic base change stuff. So we have a morphism from X to 1, and for an arbitrary object of the topos, we can pull it back to an object over X. And so we have this adjoint pair, and we can define cohomology of this object with coefficients in A as just cohomology of this slice topos with coefficients in the pullback sheaf. Yeah. So now let's let's finish this discussion by considering some examples. So first of all,
sorry, could you move to the previous slide?
Yeah.
And here the functor X sub star means forgetful functor, yeah? Or
yeah.
and the other one is a what?
Is a pullback.
Is a pullback. Okay, thank you.
Okay, so let's consider some examples. So first of all, obviously we have sheaves on topological spaces or locales, but since we didn't define what is a sheaf cohomology over locale, let's just think of topological spaces. Then cohomology of sheaf on X. So cohomology of this topos with coefficients in such a sheaf coincides with the usual sheaf cohomology of X. So as I said before, basically a cohomology of a sheaf on a topos is cohomology which is defined via global sections, because we consider home from the terminal object. So that's to be expected. Another example.
Sorry, this is a sort of a theorem or exercise.
Well, I guess it can be given a status of a lemma, but
Okay.
well, the proof is almost as I stated. So the an abelian group of morphisms from the terminal object to A, in this case, precisely coincides with the abelian group of global sections over this topological space, because one is the Yoneda embedding of X. So that is actually sort of trivial. That's precisely the Yoneda lemma. So natural transformations between the Yoneda embedding of X and A coincides with the values of A on X. So, and this is by definition just the group of global sections. So then you just say that on one hand, the Schiff cohomology of X with coefficients in A are precisely derived functors of global sections, and on the other hand, cohomology of a topos with coefficients in A are also right-derived functors of the same functor. So that's why we have an isomorphism between Schiff cohomology defined topologically and Topos theoretically.
Okay,
I don't know.
thank you.
Yeah, I hope that it's a sufficiently rigorous explanation, but I don't know. Okay, so another example is when we consider some arbitrary group. Then we can consider a topos of all its representations and sets. Then these are just sets with G action and equivariant maps. Then the category of abelian group objects in E precisely corresponds to the category of right modules over the group ring of G. The object of integers in this category corresponds to ordinary integers with trivial G action. And then we can use this description of cohomology of E with coefficients in A as an X to see that this cohomology precisely corresponds to the cohomology of G with coefficients in some G module. So as another application, we see that this Topos theoretic language allows us to encode several different things. So cohomology of topological spaces and cohomology of groups. Yet another example is given by continuous G sets. So assume that we have a topological group. And then we can consider continuous G sets. So we endow the set M with discrete topology, and we require this action map to be continuous. This basically means that the stabilizers of individual points should be open subgroups of G. Then we can consider a category of continuous G sets and G covariant maps between them. And we have an inclusion and the right adjoint of this inclusion. So an inclusion into the topos of all G sets and a right adjoint. So this is then this adjunction then induces a structure of a topos on E, and that means that we can compute cohomology of E with coefficients in A. And as it turns out, it corresponds to Galois cohomology of G with coefficients in A. So another example of Topos theoretic definition, which gives us some concrete mathematical concept. Okay, and so finally, we can consider a particular case when cohomology vanishes. And if this happens, if X is a projective object in our topos, then, well, that's basically the definition. It's projective. If it's projective, then this home functor is exact. And this means that there are no derived functors, there are no high derived functors. So above degree 0, cohomology of X with coefficients in A vanishes. And there are two particular examples of this fact. So one example is given by the fact Boolean topoi. There, an arbitrary object is projective, therefore there are no cohomology at all above degree 0. And the other one is given by topos of all pre-sheaves. So when we have a minimal topology on category C, then all representables are projective, and then cohomology of representables also vanishes. So that's another example of this instance when we compute cohomology of a projective object. And in a sense, this illustrates this idea that cohomology sort of detects the some continuous structure on our topos, because both Boolean topoi and pre-sheaf topoi are discrete in a sense. So well, this is, I guess, a philosophical reason why cohomology vanishes in both of these cases. Okay.
Sorry.
Yes. Yes.
If I suppose that the cohomology of EXA vanishes, then there is two possibilities. Yeah.
No. The statement is that if we have a projective object, then the cohomology vanishes. And
okay,
it just so happens that in both of these cases, all objects, here all objects are projective, and here all representable objects are projective. And this shows that cohomology vanishes. So that's just two examples of this general statement.
Okay. In these cases, we have that X is projective. Yes.
Yeah.
Any X.
Yeah. So here
okay.
any X, and here representable X. I guess it should denote by Y of. Yeah. I guess another example that somewhat is not as immediate is that is this theorem due to Grothendieck that cohomology on that cohomology in Zariski topology vanishes, but I'm not sure offhand that it immediately follows from the fact that affine schemes are projective. I'm not entirely sure, but maybe that's another instance of the fact that that cohomology of projective object vanishes. Okay. Well, thank you for your attention, and I guess we will discuss some more homological algebra next time, since we didn't cover any concrete methods of calculations, and it would be nice to talk about some check techniques in arbitrary topoi and stuff like that. So yeah, I hope to continue with this technique next time.